Okay, so before we start, just a reminder that you can check out a hard copy of a textbook to keep at home. You just have to return it before finals in the spring. And I'll just need to write your name down. It's super simple, and I have plenty. So if you don't like the iPad version, the PDF textbook, please come by and pick one up, all right? Today is tomorrow. I'm going to be after school on Wednesdays, it turns out. So you can come Wednesday, like right after 8th period, and pick one up, and you won't have to carry it around all day. Okay, so this first problem we're going to do is going to be kind of a review. You already did this in your homework, so I'm expecting y'all to be super quick, right? Be able to fill this chart out. This chart format here, where they give you some hints to the compound and you have to figure out the rest of the information, it's what I usually do. That means it's going to show up somewhere of importance. So this type of format you need to be ready for. So let's just go through. I need you to show work. Y'all did really good. Most of you showed work on your homework. I was nice today, but when we say on the AP exam we don't give credit for work when work is not shown, even if every single answer is correct, that is true. I do it. I grade the exam. Your teachers aren't just being mean saying show your work. The rationale behind that is we want to see the thought process. It's also important because if you miss the problem entirely, we can find something in the work that will maybe earn you 1 of 2 or 3 points. So you have to show your work, and I'm sticking to that. So if I get homeworks that just have answers in the boxes and no work shown, I'm not giving you credit for it. So, but y'all did fine today. Second period did great. All right. Yeah, I do think y'all might be my best period. So good job. So looking at this, we were given sulfuric acid, molar mass, and the number of grams. So we need to figure out how many moles and then the number of formula units we have of sulfuric acid. So we're just going to start with our mass because that is something that makes sense. 0.825, and that's grams. And then for every 1 mole, how many grams do I have? Whoops, 1 mole's got to go on top. How many grams do I have? 98. Why? Because they just gave it to us, grams per mole, right there. 98. I can use my finger now to erase. 98 grams for every 1 mole. So if you look at this, based on the given number of grams, how many moles in sig figs do we have? Nice and loud so I can hear you. That's not 3, though. Thanks. 0.00842 moles. And now I want to take that moles, which I'm going to put up here, and I'm going to convert that to formula units. So for every 1 mole, what do I multiply by? Avogadro's number. And so what is my number of formula units for sulfuric acid to 3 sig figs? I got one answer. Can someone second that for me? 5 points. I'm hearing 5.07s. And is the 23 correct? Okay, so this is not right. 5.07 times 10 to the 21st? Okay. Good. All right, so that's the first one done. The next one we're going to look at is this chromium-3 oxide. And can't do a whole heck of a lot without having the molar mass. How do we find the molar mass for this one? Correct. Use the periodic table. Find the molar mass. So to our class rule of 2 decimal places, what is it? I can barely hear. Is that Jacob in the back? I can't hear you. You're going to have to talk up. 152.00. Okay, so knowing that, we can do a little bit of work. I know that I have the number of formula units, 9.63 times 10 to the 23. That's probably going to be where I need to start. 9.63 times 10 to the 23rd. How do I get from that to moles? Divide by Avogadro's number, right? So for every 1 mole, I have 6.02 times 10 to the 23rd. And what do we get to 3 sig figs? 1.60 moles. All right, so that's moles. We have the molar mass because we just determined it on the periodic table. So how do I get to grams knowing molar mass and knowing moles? For every 1.60 moles, I'm going to have how many grams per mole? 152 grams per mole. So what would I have? 243 grams. That looks about right. All right, we good? Okay, next up is our unknown compound. I don't know it, so how am I going to find molar mass? Uh-oh, Naira. Right. Aren't the units on molar mass grams per mole, right? If you look up here, grams divided by moles, well, they gave us grams and the number of moles associated with that, so just divide it. And what is our number of molar mass per 3 sig figs? And you don't have to do the units in the table since it's on top. But okay, and the last bit here, we want to go from our 0.476 moles to formula units. So what can we do? Can we do this without writing it down now? What do we have to do to get it? Yeah, multiply by Avogadro's number. So to 3 sig figs, what do we get? 23rd? Okay. Now this last one is a single atom, molybdenum. How do I find the molar mass of molybdenum? It's 95.94. They give me number of moles, so how can I figure out grams? Set that up. I need a little more space. There it is. So I'm going to start with my grams. Oh, I don't like not being able to see it. And now I can't move it back. Okay, so we have 62.8 grams. For every 1 mole, I have 95.94 grams. So what is my number of grams? No, this is, yeah. No, what am I doing? Is this moles? Yes. Oy. Sorry, people at home. Having one of those days. So it's 62.8 moles. Okay, let's reverse that. For every 1 mole, I have 95.94 grams. So moles cancel. How many grams do I have? The 3 sig figs. Give me 6 what? I heard you, and then someone talked over you. So 6,030. 6,030. All right, is that good? All right, the last box. What do I have to do to fill this in? Multiply that number of moles times Avogadro's number. So to 3 sig figs, what do we get? All right, so that's how we fill those tables in. This was just a crash review from yesterday. If Is everyone pretty comfortable with all those conversions? Okay, let's move on. We're going to hit multiple topics today that are all review, and I'm going to do 1 or 2 problems for each topic, and then you'll be able tonight to do a little bit more practice on all of them. So the first one, which is super simple, and we're only going to do 1 problem, is percent composition. Percent composition is what percent of each element exists in the whole compound. So it's just a percent, which is part over whole times 100. And it's by mass. So we are going to find the percent of each element. Normally on the AP they only ask, what's the percentage of oxygen and blah, blah, blah. It's not all the elements, but just for practice, we're going to do all the elements. So we want to find the percent of nickel, phosphorus, and oxygen. Most importantly right now, to make this work, we need the full molar mass of the whole compound. We want the whole. So you guys go ahead and calculate nickel 2-phosphate's molar mass while I set up a cute little table. All right, so what is our total molar mass? All right, 366.04. Of course, I wrote it 2 times, so of course it's wrong. What is it? Is that right? What'd y'all get? Someone didn't, because 2 people just stopped me. So what did those people who stopped me get? Did anyone else get 365.74? Did more people get this? 366. Okay, we're just going to go with that. 366.04. Okay, so now that's the total. So we now need the part. And by part, we're looking at first nickel. We need all the nickels, not just 1 nickel. There are 3 nickels in this compound. So what is the mass of 3 nickels? 176.1. Who's speaking? Okay, 176.1. We're going to take that, multiply it through, and there are no set sig figs on a problem like this. For decimals, for decimal places, for percents, I just like to carry it out to 2 decimal places. So let's just do that. As long as you're consistent, I don't really care what you do. Just be reasonable. I don't want whole numbers, obviously. I'd like some decimals, 1 or 2. Go ahead and tell me the percent. All right, phosphorus. How many phosphoruses are in this? 2, so it's 61 point what, Rui? 0.94 divided by the original 366.04 times 100. What do we get? 16.9%. All right, in oxygens, we have how many of them? 8. So 8 times our 16, 15.99, 16.0 is 8 times 16? Oh, you did the percent. Tell me the number. All right, 128 grams per mole for that, and that's 35.0%. Looks to me like that came out to 100. Yay, some things worked out. All right, so that's percent composition. Super simple. Any questions on it? Any things you can think of that might be problematic? Okay, now empirical and molecular formulas. Who remembers the difference? Anybody, anybody, anybody? Isabel. The empirical formula is the lowest you can reduce it to, meaning it's the lowest whole number ratio, okay? And molecular formula, we know, is going to be some multiple of that. But what's the significance of the molecular formula? Naira? Yeah, you know the total mass usually. Whenever you're given a mass, it's usually of the molecular formula. But why do we care about molecular formulas? Because that's how they exist in nature, okay? So empirical formulas are the whole number reduction of those subscripts. Now, sometimes the empirical formula and the molecular formula are the same, like H2O. Is that the lowest possible whole number ratio you could have? Yeah, and that's also how it exists in nature. So sometimes they're the same, sometimes they're different. So when you're doing these problems, what I want you to do is, you guys don't know more chemistry than the exam does, so don't be rearranging the percents. And as I say that, I'm going to rearrange the percents and put carbon first, then hydrogen, then chlorine, because this is just a bad problem. So whenever you're given a problem on a test, on a quiz, on an AP, write down the percents in order that they appear in the problem and then go from there. So I want to start with carbon, and it's 24.27. And I'm going to change that percent to gram. Anyone know why I can do that? Yeah, we're assuming 100 grams. So if we assume 100 grams of compound, that's how many grams of carbon we'd have. And remember, we're dealing with ratios. So as long as we treat all these the same, we are good to go. Our H is 4.07 grams, and our Cl is 71.65 grams. I just know the compound is written this way because of my organic chemistry knowledge, but I just want you to always follow the order in the problem. All right. The first part of this is always to convert grams to moles because we need the whole number mole ratio. So, if you're having issues converting to moles, remember, it's always grams divided by the molar mass, 35.45. So, you don't have to set this up every time. I'm hoping, kind of, in AP, that you're able just to do the division straight up and not have to do dimensional analysis for something as simple as going from grams to moles. Okay? But if you need to set it up this way, do it if you're confused. For this, it's 12.01 grams per mole. Okay? So the more and more you do this, the more apt you are to do something like that. So carbon. Now, to make these numbers work, we want quite a few decimal places, at least four or five. Don't sit there and round this to one decimal place, then your numbers are going to be all weird. So what is our number of moles here? 2.02. Okay. That's moles. All right, how many moles of hydrogen? Okay. And then how many moles of chlorine? All right, so okay. So now what we're going to do, now that we have all these different moles, to find the mole ratio, the lowest mole ratio, what am I going to divide by? The smallest of all the moles in the land. And that would be this one, 2.020816. So we know that's going to divide and get 1, right? 2.020816, that's going to divide. And what do we get? What does the calculator tell you? Yeah. That's not going to change anything at this point because we're dividing by 2.02. It's going to come out to be 1. So so this comes out to be 1.994. You see how close that is to actually being 2? This is an allowable rounding. Where I don't allow rounding, well, not me, where you're not supposed to round, if it's like 0.75 or 0.8, that's too far to round. That's going to mean you're going to have to multiply through by some sort of number. Okay? So if these don't come out pretty gosh darn close to whole numbers, you'll have to do something to make that happen. And we'll address that in the next problem. But for now, we're just going to round this to 2. And this one, no matter, Amelia was saying there's an issue with this number, it doesn't matter enough to change it. It's going to be 1. It's really freaking close, right? Okay, so my ratio now is CH2Cl, right? This is my empirical formula. Now, one thing they gave me was the molar mass. Whenever they give you the molar mass, folks, that is the molar mass of the molecular formula, not the empirical formula. It might be the same, but it might not. So what I like to do is kind of make a little chart. My goal is to find the molecular formula, right? The molecular formula's weight is given to me is 98.96. To figure out how many times greater the molecular formula could be, I need to know the empirical formula's mass. What is the molar mass of our newly improved empirical formula here? .48. Do you see the relationship between these two? The empirical formula is half, or the molecular formula is doubled. If the molecular formula is doubled, you see that it's doubled. It's going to have to be a close whole number ratio. And here's something when you get to AP level problems. You know, the math is going to be a lot more crazy because we'll see it in the next problem. You're going to have more expectations in what's going on. If you get an empirical formula that isn't evenly divisible in the molecular formula's mass, you did something wrong. And that's the best thing to know because you can stop yourself from making a huge mistake. Okay? I remember y'all having some of these on last year's test and people didn't catch on to that. Okay? You need to be able to get a really, really, really close multiple, like almost on the nose for it to be done correctly. So this is 2, pretty much dead on, right? So what is the molecular formula then? And I could draw that for you. It is a legit compound. Okay? All right, let's go ahead and do another one of these. This one's done correctly, so we can write it in the order as given. Determine the empirical formula for a compound which is 26.6% potassium, 35.4% chromium, and 38.1% oxygen. So we're going to make all these percents grams, right? And we're going to divide by what? What are we dividing by? The molar masses to get the moles. So chromium is 51 or 52.00. This one's 16. Potassium, I don't know the decimals, 0.10. So there's my molar masses. Again, these are in grams per mole, so we'll end up with just moles after the division, since those are grams. So what is our potassium moles? Whoa, 0.68. All right. Chromium. Oxygen. Okay, so now we have all our moles. So what do we do with these moles? Divide by the smallest, which is pretty much point. So just divide by, just to make life easier, 6803. All right, so this is a 1 for sure. What's this guy? It's a 1, right? It comes out to be 1.9 something, 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 something. Now this is the one we need to talk about. What does your calculator say? 3.5. All right, we cannot write our formula. Can't do that. And we can't round. This is actually a great problem because it's on a 0.5. There's not a lot of decision making to do. So what do we have to multiply this whole formula by to get whole numbers? 2. You got to have whole numbers here. So when you multiply by 2, your empirical formula ends up being what? K2 Cr2O. Does that look familiar? That's exactly. Dichromate is Cr2O7 -2, right? So how sexy is that? That worked out. So that is the empirical formula. Now the question they have is, what's the molecular formula? Well, we know the molecular formula's mass is 294.2. So we need to know the empirical formula's mass. We need to solve it. What is the empirical formula's mass? 294.2. So, are we done? Yeah, this is the empirical formula and the molecular formula because the mass came out to be the same. So, how do you know you did this problem right? It's because we came out with a molecular formula that matches this empirical formula. If you would have decided to round this to 4, I'm going to kind of do this on the side, and got CKRO4, because that's how you roll, someone find that molar mass for me really quick. So 155. Take 155 and divide it into 294. What's 294 divided by 155? What is it? Yeah, you got a 2.5 for a difference between an empirical and molecular formula? You can't do that. So that's when you tell yourself, I made a mistake somewhere. And you go back and you redo that empirical formula. Okay? When you divide these two numbers, they need to be dead on a ratio, like a 2 or a 3 or a 1 or whatever, a multiple. Okay? All right, so now you'll get to, for the homework, get to look over some empirical formula stuff for practice. When you get to, I'm not done yet, but while I'm thinking about it, number 6 is a combustion analysis problem that I'm actually going to do in class. So look at it, set it up. See what you can, I want you to pre-think it. I want you to think about, okay, how could I do this? But if you can't do it, don't freak out, because we're going to cover it. But I'm going to see who can get it on their own. Okay, balancing in stoichiometry. So we want to make sure we know how to balance equations, and then we want to be able to do stoichiometry. So number 29 is just balancing and drawing some stuff. So let's take a look and try to balance this. This is the combustion reaction. I always save my oxygens last when I'm balancing for combustion, so I take care of the C's. So I need a 2 there. And then I'm going to take care of the H's. I've got 6 H's on the left, so I need to put a 3 there. Now I'm going to take care of my O's. I've got 7 O's on the right, correct? So look, last period I messed up because I forgot that O. That O right there makes me only need 6 more, correct? So I'm going to put a 3 here to balance. So now we'll draw a particulate diagram to represent all reactants and products, and you can then see balancing that way as well. This is going to seem like it's baby, but you need to be able to draw stuff. So for the 3 atoms represented, I'm going to draw for the carbons a solid, and then for oxygens, I'll draw lines, and then hydrogens, I'm just going to do little baby clear balls, okay? And I should have drawn, let me draw, I'm going to make carbon a tad bit bigger, because carbon is a bigger atom than oxygen. Okay. All right, so I want you to connect these as they're supposed to be connected. So this is an ethanol. My carbons are connected in the carbon chain, so I'm going to have carbon-carbon connected like this. Particulates don't have sticks in them. They're usually just balls like this. So there's my carbon to carbon. Any suggestion of what I need to do next?
Well, the carbons, do they have like 3 open spots like other atoms?
Yes.
Do they like touch each other?
Perfect.
You could put the oxygens there?
The oxygens.
Or rather, or I guess you can start putting the hydrogen.
Let's start with the hydrogens. Now the OH is one group that's attached in one spot. It's not an O and an H to carbon, it's an OH. So I actually want to start there. And I'm going to put my OH group, so I'm going to do the oxygen and then the hydrogen. That's the OH group. So now I have 5 hydrogens to put on there. And like Rui said, each thing has 3 slots, 3 extra slots, or 3 extra bond possibilities. So I'm going to put a hydrogen and a hydrogen, and then 1, 2, 3. And that's 1, 2, 3, 4, 5 hydrogens and the hydroxyl group. See it? All right. And to that, we're going to add, how do I draw O2? It's just 2 O's attached, right? Don't forget, they have lines. So we got 3 of them, though. Those are my O2s. And I'm going to make 2 CO2s. So I've got my C's, and I'm going to put 2 O's on them. O, O, and put lines in them. O, whoa, O, O. And then I need 3 waters. Water's easy. Water's just an oxygen with two little Mickey Mouse ears. Oxygen, Mickey Mouse ears. So if you know the shape of the molecule, you might as well just kind of draw it like it's supposed to be. I know that carbon dioxide's linear, so I kind of drew it that way. I know that this looks like that, Mickey Mouse ears, water does. Okay, we good with that? All right, let's do number 30, which is the beginning of stoichiometry. Those of you who had me last year, I was not here for this unit, so I'm really glad I get to teach you stoichiometry my way. And I try to make mine really simple in order to cut down on the amount of reading you have to do. Some of the problems get pretty long. So as you're reading the problem, I want you to jot things down in a certain way so you don't have to keep going back up. What am I looking for again? That kind of thing. So I'm just going to go through this as I would be going through this. Determine the amount of iodine. I am determining the amount of iodine. And it's probably going to be in grams. So I put a question mark with a gram. So I know I am looking, that does not look like a question mark. Let's try it again. I am looking for iodine. That's the point of the problem. When 145 grams of Ki, I'm going to put that under Ki, or on top of Ki, whatever, react with excess copper 2 chloride. That's an excess. So this is not a limiting reagent problem. We don't have to figure out what's limiting. We know that this is an excess, and we're going to use the Ki. Now, due to the fact we're going from one reactant to a product, we're actually going to do stoichiometry. I call it the mole bridge. You can mole bridge anywhere because all of this is based on the ratio. There's 2 of these to 4 of those to 2 of those to 4 of those to 1 of those. We can go from reactant to product. We can go from reactant to reactant. We can go from product to reactant. Doesn't matter as long as we use the mole ratios. So I call this the mole bridge because what do you have to be to get on the mole bridge? You have to be in moles. So we're going to start a long dimensional analysis, and it's really important when you're doing stoichiometry that you write the unit and the compound because we're going to change compounds mid-dimensional analysis. So I'm going to start with 145 grams of Ki. Now I can't get on that mole bridge until I am moles. So for every 1 mole of Ki, how many grams do I have? 166 grams. All right, so my grams of Ki cancel, and now I'm in moles. So now I can cross the mole bridge. The mole bridge is that mole ratio. I think about gatekeepers here. 4 to 1. Those are the gatekeepers to cross the bridge. So for every 4 moles of Ki, based on that 4 here, I have how many moles of iodine? 1 mole of I2. Now I need, am I done? Nope, I got to get to grams of what I'm looking for. So for every 1 mole of I2, I have 253 point what? 8 grams of I2. All right, so to the given 3 sig figs, how many grams of I2 do I have? 55.4 grams of I2. So how do y'all feel about that? Not too bad. We'll do a couple more. Okay. I really like this next problem because it's something that applies to real life. It says baking soda is often used as an antacid, and it gives you the equation. And then they're like, okay, milk of magnesia is also an antacid. So you've seen milk of magnesia at the store, right? It's like Pepto-Bismol. They have some, it's got magnesium hydroxide in it. Do y'all know what I'm talking about? Okay. Yeah, y'all are like looking at me like I'm freaking crazy. Baking soda was an old-timey remedy. Like that's what, before they used these specialized products, they used baking soda. You had it at home, you put it in water, you drank it. It tasted horrible, but you felt better. Your stomach felt a lot better. So the question we're going to find out is which is more effective per gram of these two? So if I'm going to compare, I'm going to compare the same amounts, right? I have to compare the same amount. I can compare as much as I want, but I'm just going to do a gram. Now, what is the job of these things again? Antacids, what do? Neutralize acids. So we care about how much acid this reacts with, right? So where do you think we're going to stoich to? Where are we going to mole bridge to? The acid, which is the HCl. So we're going to mole bridge over to there. And you can take it all the way to grams of HCl if you want. I say we just take it to moles because we can compare moles. So the question is, which one is going to react with more moles? So this is 2 stoichiometry problems. Let's do the baking soda first. All right, the baking soda, if we start with 1 gram of sodium bicarb, what do I have to do to get on the mole bridge? I got to convert to moles, so we need the molar mass. So for every 1 mole of sodium bicarb, I have 84.01 grams. So my grams cancel. Now I can do a little mole bridge action. For every 1 mole of NaHCO3, I have 1 mole of HCl. So what do we get? How many moles of HCl does this neutralize? That's fine. 1 sig fig's fine. That's all I gave you. 0.01. 0.01 moles of HCl is neutralized. Does everyone get that? That's what stoichiometry is. It's telling you what's reacting with each other or how much is being produced depending upon where you're going with that arrow. So now let's try this antacid. We're going to do milk of magnesia. It also makes you go poop. Milk of magnesia. It isn't just an antacid. It also makes other things happen. Yeah, when I was on chemo and I was on all these drugs that made you not, drank a lot of that. Yeah, good times. Good times. All right, so start with 1 gram. I know I was an overshare and I did it on video. So that's awesome. All right, magnesium hydroxide. It's all right. It's real life. Our bodies are real life. Nothing. We all do it. Every single one of you, unless you're from another planet. All right. For 1 mole of magnesium hydroxide, what's our molar mass? 58.333 grams. Now, some of you might have caught on and like, oh, there's more moles of acid, so obviously, you know, you need more of whatever. You really can't just look at it and tell because of the differences in the molar masses. You really just need to do the math to check. So our grams cancel. And then what's our ratio? For every 1 mole of magnesium hydroxide, we have 2 moles of HCl. Okay, so magnesium hydroxide neutralizes more moles, but it weighs less. So we don't know until we get the math what is our actual moles of HCl neutralized. Ah. All right, so which are you going to take? Milk of magnesia. That's going to do a better job than sodium bicarbonate. Okay? Good? I like real life problems. Last problem is a last real life problem. Before I change the slide, anyone have questions? Okay. This is kind of cool. An industrial method for the production of elemental zinc from its ore is to roast the ore and then throw some carbon monoxide gas on top of it to isolate the zinc. So it says a 10 kilogram sample of an ore containing zinc sulfide was chemically treated with those reactions, producing 2.85 kilograms of zinc. Determine the percentage of the ore in the original sample of, percentage of zinc sulfide in the big piece of ore. So you're a miner, and you go into a mountain and you dig out a 10 kilogram sample. Within that sample, there are spots of zinc sulfide. Okay? When you put this whole 10 kilograms through this process, you end up producing 2.85 kilograms of zinc. So the question they want to know is, what percentage of this is actually zinc sulfide? Okay. Let's forget about this percentage for a minute. This 10 kilograms we're going to deal with at the end. But what we do need to figure out is how much zinc sulfide is needed to make that much zinc. So we're going to do dimensional analysis stoichiometry through two different equations, which is totally cool, because there's always going to need, but there has to be a connection. What is our connecting compound between the two? Zinc oxide. So that's what we're going to stoich to originally, and then do mole ratios until we get to grams of zinc sulfide. So I'm not a big fan of kilograms when we're doing this stuff because, hello, we're in grams per mole up there. So how many kilograms of zinc, how many grams of zinc is 2.85 kilograms? 2,850 grams of zinc is what we're going to start with. So in order to mole bridge, because we want to now mole bridge over to that connection, that zinc oxide. To mole bridge, we got to convert grams to moles of zinc. So for every 1 mole of zinc, I have 0.41. All right, that's grams of zinc. So grams cancels. Now I'm in moles of zinc, and now I can mole bridge through to get to ZNS. So for every 1 mole of zinc on the bottom, how many moles of ZNO do I have? 1. All right, so now I look at the relationship between ZNO, and remember, we're looking for percentage of silver sulfide, so I need grams of zinc sulfide. Why do I keep saying silver? Zinc sulfide. So for every 2 moles of ZNO, I have 2 moles of ZNS. Yeah, I know it's 1-to-1. I got that, but I'm writing 2 down because I want you to see where I'm getting the numbers from. And now that I'm out of room, what do I need to convert this to figure out percentage? Grams. So for every 1 mole of this, how many grams of ZNS do I have? 97.48 grams. All right, so long dimensional analysis problem. It's actually not. It's just 2850 divided by 65.1 times 97.48. And what is our grams of ZNS? Give me 3 sig figs, please. What? 4,250 grams of ZNS. Well, that's how much ZNS was in that big chunk of rock. So how do I get the percent? Part over whole. How much does the whole rock weigh in grams? 10,000 grams of ore. That's part over whole times 100. So my percentage is 42.5%, right? So that rock was almost half ore. Isn't that cool? I like stuff like that. All right, so tonight's homework's important because it's again, it's your foundation of basics. So be sure to work on it. Don't freak out about number 6. Just give it a whirl, and we'll talk about it tomorrow.